Okay, today I'm going to talk about section 4.1, the indefinite integral. One of the things that I talked about earlier in the year is really when it comes down to it, calculus is three big ideas: limits, the derivative, and so we've talked about both of those quite a lot. And the third is integrals, and today we're talking about the indefinite integral. I will tell you that we're not going to have a lot of context today. Really, we're going to be focusing on the algebra of the indefinite integral. And then as we move through this chapter, we'll get more context of what these things mean. So, first of all, take a look at what I have here. Notice I have capital F and lowercase f. So we are talking about something that is case sensitive for these particular problems. So what we're doing here, if we take the derivative of capital F, we get lowercase f, okay? So this is what's called an indefinite integral. We'll then talk about what a definite integral is, but this is an indefinite integral. So we get kind of like this fancy S sign, f of x and dx. So it's almost like these are part of an operation, the integral and the dx. This is what we're integrating, okay? This is what's referred to as the integrand. And these terminology I'll use. It's not necessarily something you'll be tested on, but this is what is referred to as the integrand, and this is the variable of integration. I will tell you that most of the time you don't think much about this, but the dx is part of basically the operation, if you think of it that way, of integrating. Okay. So if I take the integral of f of x dx, what I get is capital F of x plus c. And we call this capital F of x plus c, we call this the antiderivative. So in other words, if I take the derivative of this, I get this as I have up here. Let me just talk about this plus c. This is what's called the arbitrary constant. Just understand that if I take the derivative of something, all constants go to 0. So if I do the antiderivative, I lose constants. So for instance, let's take a pretty basic example. Let's just take y equals 2x. Okay. Let's say I want the antiderivative of that. So let's say this is the derivative. Okay. So the antiderivative of that would be x squared, right? And if I take the derivative of this, I get 2x. But we put this arbitrary constant. And the reason why is because you could add anything to that, and anything added to that, if I take the derivative, would end up zeroing out. So technically, depending on what c is, there's actually an infinite number of antiderivatives, functions that if I take the derivative, I get 2x. Now graphically what that means is, if I look at 2x, which looks like this tells us all the slopes. So there are an infinite number of functions that have that slope. One of them would be, something like this, right? So this would be the original, and that would be y prime, okay? But you could also have something that looks like this, right? So any possible thing that has that general shape, and I can shift that up and down, and that basically algebraically is that plus c. So I don't know, I might have mentioned this at different times, but just keep in mind that derivatives don't actually give us values, right? They only give us the general shape. In order to get values going from a derivative to the original function, you need some point to sort of lock that in place, and we'll actually be seeing that later in this video. But for the most part, if I just give you the derivative, I can get you the general shape of the original function, but we're always going to have this arbitrary constant. Okay, like I said, today's going to be all about finding these antiderivatives, so it's going to be very algebraic. So we'll get started on some examples, and really we're going to be reversing what we've been doing basically for most of the year. Okay, so I have a few examples up here, and we're just going to keep doing examples. I'll do my best to sort of explain what's happening here, but the reality is that you're not really going to start getting comfortable with this until you start practice this in your groups. It is a little bit different. So basically, with all of these, as I talked about the integral, we want to think it's the antiderivative. So we're reversing the derivative process. So one thing I like to say is you literally have to know your derivatives forward and back, because not only do we take derivatives, but we take antiderivatives. So we have to go forward and we have to go back. So we'll start out with a few polynomials here. So let me just point out, normally when we take the derivative of something like this, we use power rule. The exponent comes down, multiplies by what's in front, and then that drops a degree. So if I reverse that, we want to start with this and realize that I'm going to raise that a power. Normally I drop that degree. Now here's the thing, if I'm taking the derivative of this, right, that 5 is going to come down and multiply, but I have a 1 here. So what I need, whatever I raise that to, I need the reciprocal of this out front. So when that 5 comes down, it's going to cancel with that, bring us back to 1 and then x to the 4th. And then the derivative of 3 will just be 3x. The derivative of 3x is 3. And then don't forget your arbitrary constant. Now one thing at this level, what I suggest you do until you get very comfortable with this, is definitely give it a check. So let's take the derivatives, and whether you write it on your paper or not, that's not all that important. But so 5 comes down, 5 times 1/5 gives us 1, x to the 4th plus 3, and there you go. So take your derivative, and then, or excuse me, take your antiderivative and then check it by taking the derivative. Okay, so now this one we need to rewrite first. So we'll call this x squared. So that's x to the 2nd power, and then the 5th root. So that gives us a fractional exponent. Now we have to think about that. If I'm raising that a power, really what I want to think of is, so if I'm adding 1 to this, I'm adding 5 halves, right? So this is going to give me x to the 7 halves. And then once again, keep in mind that I need the reciprocal of that out front. Yes, so that will cancel, and don't forget the plus c. Now once again, let's give that a check. 7 halves comes down, that does cancel. Drop a degree, that gives us 5 halves, and of course the c zeroes out, okay? So these are our indefinite intervals. Okay, taking the antiderivative of any constant is quite easy, because it's just going to be 4x plus c, and then of course it's easy to see that if I take the derivative I get 4. Okay, this one, so let's think about this. So raise x a power, so that will be x squared. Now normally I would have the reciprocal there, but realize there's already a 2, right? So even if I did put the reciprocal there, it would be 1/2 times 2, which would be 1. What's important is I see that when I take the derivative I get that 2, and then minus x, and then plus c. Give it a check. 2 comes down, that drops to 1. Okay, there we go. The derivative of negative x is negative 1, and the derivative of c is 0. So we're all good there. Okay, let's raise this a power. So this will be x to the 4th. I need the reciprocal of that in front, so when it comes down, it multiplies, giving us back 1. Minus, raise that a power, that's 2. Now let's think about this one. This one's a little bit different. What number would I put there so when it multiplies it gives us 4? And that's going to be 2, okay? And then minus 7x plus c. And I will tell you that at first for some of you, this is going to seem like writing with your non-dominant hand. You're sort of getting into this process of reversing all these things that we've done. At first it might seem unnatural because it's just not something we really focused on. But with practice, you'll get better at this. Okay, now the integral of secant squared x, really with any of our trig functions or transcendental functions, these are typically going to be from right off our derivative page. So I don't give you a list of integrals because it's just the flip. So if you think back to all your derivatives, sine, cosine, tangent, etc., we remember that the derivative of tangent is secant squared x. So that means that the antiderivative of secant squared x is tangent x plus c. So once again, you need to know your derivatives literally forward and back. So that's our antiderivative. Okay, so let's continue on. We'll do some more examples here. Like I said, nothing but algebraic examples today. Okay, let's continue on. Have a few more examples here. These ones are a little bit different. So let's look at this first one. Now, what I'll tell you is anytime I have a constant, one thing you can do with integrals, and this is actually true with derivatives, that any constants that are in the integral, I can actually bring out front and sort of deal with that. Just like if I'm taking the derivative of something and I have a constant, I can keep that constant out front and take the derivative, and that's fine. So that works forward and back. So what I'm going to do here is I'm going to bring out that 1/2. And I get 1 over x dx. Now once again, If you really know your derivatives, literally forward and back, hopefully you remember that the derivative of ln of x is 1 over x. So that means that the derivative of 1 over x is ln. Now, one thing, and I'll talk about this in class, it's actually just not x, it's the absolute value of x. Don't forget the 1/2 in front, plus c. And the reason why is the domain of this is all reals, x not equals 0, which matches up with that domain. If I didn't have the absolute value, these domains wouldn't match. This domain would be just the positives, while this one is all reals, x not equals 0. So if we have that single degree in the denominator, it's going to give us ln an absolute value of x. If you forget the absolute value, that's something I'll give you some time to sort of polish up. Okay, so let's look at this one. Once again, that constant, I'm just going to go ahead and bring that out front. Okay, and now let's call this x to the 2nd power over 3, and that's going to be a negative. Now, this is different though. So please, sometimes people make the mistake of going, oh, that's ln of that thing. No. That's only if it's degree 1 in the denominator. If it's any other degree, then we just reverse that power rule, just like we did with the problems on the previous page. So we have x to the negative 2/3. We're going to raise that a power if we need to. Just think about adding 3/3, right? That's adding 1. So that's going to give me x to the 1/3. Okay. I still have this 3 out front. What do I need in front to cancel with that? I need a 3. So this is actually going to be 3 times 3, which will give me 9, right? So and then plus c. And then once again, if we take the derivative, just keep in mind that 1/3 comes down. 1/3 times 9 gives us 3. And then, of course, if we take the derivative of a constant, we get 0. Now, if you left this as 3 times 3, that's perfectly okay. Just like when we were turning out derivatives, simplification is not a big deal with these until perhaps we have to work with them. Okay, number 9, and actually 10 as well. At least not yet, we don't know how to integrate products or quotients for that matter. So we have to find a way to write them so they're not products or quotients. So you might remember before we learned product rule and quotient rule with derivatives, we would do this process of rewriting things. Like we wouldn't take the derivative of something like this, we would multiply it together. And that's what we're going to do here as well. So if I multiply this together, okay, and you can use whatever method you want. I recognize that this is a difference of 2 squares, so I'm just going to call that x squared minus 4. So I'm rewriting this thing. Now, take the antiderivative. So we're going to raise that a power. That goes to x to the 3rd. I need a 1/3 out front, so when that comes down, it cancels. Minus 4x plus c. And then let's do that check. 3 comes down, that gives us x squared. The derivative of this is 4, and the c goes to 0. So we are in business. Okay, so do those checks, especially when you're first starting off with this. Just takes a moment usually. If you write it down, great. If not, it's not a big deal. All right, same thing here. I got to distribute this thing before I integrate it. So this will be 12x squared minus 14x dx. Now take the derivative. We're going to raise that a power. That will be 3. Now what number do I multiply 3 by to get 12? So that's obviously 4. This will be x squared, okay? And what do I multiply 2 by to get 14? That is 7, and then plus c. By the way, if you ever get confused with this, you can always just keep that number out front, and then if we're raising this to a 3rd power, just have the reciprocal there, and then if you combine that, you can see, or you could even leave it like that, even though that's a little cumbersome. Okay. Number 11, hopefully this is something we're getting used to. If we have a division like this, multiple things on top, single thing on bottom, I can break that into 2 parts. So I can call this x to the 3rd over x squared plus 3 over x squared dx. Now, once people learned quotient rule, when they were taking derivatives of things like this, they were often just using quotient rule. Typically with derivatives and integrals, it's better to split them up like this. It's going to give us an easier derivative or integral. It's also usually going to be easier to work with. So now x to the 3rd over x squared, that's just going to be x plus, and then this, I got to use a negative exponent. Okay, now take the antiderivative. So we're going to raise that a power. That goes from 1 to 2. I need a 1/2 to cancel with that. Raise that a power. Negative 2 raised to the power will be negative 1. Now realize if I bring that negative down, I need a negative to cancel, so this will be negative 3. Okay, so when I take the derivative, okay, so that works. And then finally do your check. And there you go. All right, So I have two more examples for you. These are what are called differential equations, and that will be it. Okay, example 12. Find the particular solution that satisfies the differential equation given the initial condition. So when you're asked to solve a differential equation, it's not like solving an algebraic equation where you get something nice like x equals 4 or x equals negative 1/2 or something like this. When you solve a differential equation, you're starting with an equation and then you're getting another equation. The term differential equation just means, think of it as a derivative equation. So this is a derivative. When they ask you to solve it, we want to go back to that original. We want to go back to f of x. Now, the reason why they give us this initial condition is without that initial condition, we can't find the particular solution, the one and only solution that passes through that point. Otherwise, we're going to have what is called a general solution, which there are going to be an infinite number of possibilities for that. Okay, and I'll talk about this. So in other words, what we want to do to get f of x is we want to integrate this. Okay, so the derivative of this, we're going to get the antiderivative will be f of x equals, okay, so we're going to raise this a power, so that'll be 2. What do we need in front? So then when I multiply by 2, I get 10. Well, that's 5. Let's raise this a power. That's going to be 4. What do I need in front? So then when I bring that down, so that's going to be a 3. And don't forget we need a minus here, and plus c. And just like I was doing with the other examples, we do want to quickly take the derivative and make sure it matches. Okay, now this is what's called the general solution. So this is what's referred to as the general solution. The general solution, there's actually an infinite number of possibilities because of c. So if you think about the graphs as I talked about when I began this, think about all those possible graphs shifting up and down that give us this derivative. Okay, so this is what's called the general solution. So just some terminology. So if you're asked for the general solution, that means we have the plus c in it. The particular solution means we're going to plug this point in and solve for c and get the one and only solution that passes through that point. Okay, so this is going to be f of 2. So I'm plugging 2 in everywhere I see an x. And the output of that is negative 1. So 2 to the second, that is 4, so this is 20. Minus 2 to the fourth is 16. 16 times 3. Okay, I made a mistake on my, sorry about that. I made a mistake on mine. So let's see, that's 16. 16 times 3 is 48. Let's see, let's just double check this. 2 comes down, that's 10. 10x squared minus. Okay, that looks good. All right, so I think I'm good. So 2 goes in, negative 1. So this is 16. 16 times 3 is 48, plus c equals negative 1. So then I get, I want to solve for c. So c is equal to, so 20 minus 48, that is negative 28. Negative 28, we'll add that to the other side, so this will be 27, okay? So then if we plug that in, so we got c is equal to 27, we get what is called the particular solution. So this is 5x squared minus 3x to the fourth plus 27, and this is what we refer to as the particular solution. Okay, last example for today. We have a differential equation. This one's a little bit different. It's a double derivative. We have 2 initial conditions because basically we have to go up the ladder twice. So we go up the ladder once, that will give us f prime, then we can use this to find c. And then we go up the ladder again, that will give us f, and we use that to get the c in that case. Okay, so let's do it. So f of x, f prime of x is going to be the integral of sine x dx. Now this is where things get really, really confusing because a lot of times people think, oh, okay, so the derivative of sine is cosine, positive cosine. The derivative of cosine is negative sine. When you integrate, when you antiderive, those actually flip. That's why these checks are very important. So f prime of x, the antiderivative of sine x, is actually negative cosine x. Because if I take the derivative of cosine x, I get that negative, so I need that negative to cancel and get us back positive. So sine and cosine kind of flip when we do antiderivatives. So one of those things we have to get used to. And as I said, these things at first might not be all that natural. With time, hopefully, we will sort of figure these things out. Okay, now we got to get the C here. We're going to get the C here by plugging in our initial condition. So f prime of 0 is equal to negative cosine of 0 plus C is equal to 1. So realize cosine of 0 is 1, so I get negative 1 plus C equals 1. So that means that C is equal to 2. So now let's plug that in. So we have f prime of x is equal to negative cosine x plus 2. So that's going up the ladder once, but now we have to go up the ladder again to get f of x. So that will be the integral of negative cosine x plus 2 dx. Okay, so this is the antiderivative of negative cosine will be negative sine x, right? If I take the derivative of negative sine x, I get negative cosine x. Definitely want to do those checks until you get really good at this. Plus 2x plus c. And then finally, we're going to use this point to get our c here. So f of 0 is equal to negative sine of 0 plus 2 times 0 plus c, and that's equal to 6. Actually, this works out really nice because sine of 0 is 0. 2 times 0 is obviously 0, so we get c is equal to 6. Oh, by the way, just once again, this is what's referred to as the general solution. We want the solution particular to this point. So now I just put it all together. Our particular solution is f of x equals negative sine x plus 2x plus 6. And there you go. This is the particular solution. General solution, particular solution. Okay, so that is it for 4.1. As I said, we're going to be practicing this algebra. Down the line, we'll be talking about the applications of the integral and give it some context. Today, we're sort of working on the nuts and bolts. All right.